Hello, everybody. Welcome back to our discussion in dynamics. Today we'll start a new topic, which is work energy methods for particles, as you all can see in here. So let's place us this topic in our timeline. So we are here, and that means that we are done with these two topics, with kinematics and kinetics. But it doesn't mean that you should forget everything about kinetics and kinematics, okay? Because I think that these topics will come back in here even, in here, and maybe even in the second part of our semester, okay? There might be some, in other words, there might be some examples that combine, for example, work energy and kinetics, okay? We will see. I just remember doing such examples in the past. All right, and plan for today, brief lecture review, example number 1, example number 2. So what I would like to talk about here. So this will be a review. And I would like to start with our old good friend particle P following the trajectory, okay? So we have our particle, exactly the same particle, and that particle follows this trajectory, and there is also some force acting on that particle. Force. And last discussion, I said that this is a net force, but I think I was wrong, actually, you know? I wrote that last discussion, last hour, 1 hour ago, net force. However, I think it's not true, because net force has to be pointing along this direction. Okay, it has to be pointing in this direction, yes. So to all of you who are watching this 1 hour after, I mean, for all of you who are watching, who are in my other discussion, sorry. I will try to correct myself next week. Yeah, so let's say that this is just a force F, okay? Some force F, let's not say anything about it anymore, okay? And you guys remember that our acceleration can be obtained from this expression, F equals to ma, okay? And we will start from that expression, and we will derive this expression, T1 plus U12 equals to T2, okay? So there's a relationship between those two expressions, right? And before we start our derivation, I have a question to you. Why this is true? Because I think 2 weeks ago, we said in our discussion that F equals to ma. But I think that we never said why it is F equals to ma. So maybe any of you can tell me, why this is true. Why F equals to ma is true. Anybody wanna go for it? Do you understand the question? Yeah, because it took me a while to understand that question actually. But I'm not gonna reveal much. Why F equals to ma is true? Why, if we have a particle of mass m, and I apply force, the resultant will be acceleration. Why? Excuse me? Yeah. Yeah. Okay. Yeah. We will see. We'll see. Yeah. Anybody else wanna go for it? I didn't say it's wrong. I said we'll see. Yeah. And this is what he said. So. Have you ever thought about it, guys? Yeah. Also, I would, Christina. Yeah. Mm-hmm. Yeah, that's true. And but exactly why it has to obey that law. That you are correct. Yeah. Okay. That's you are kind of repeated what Tom said. Yeah. Exactly. Yeah. Yeah. So we have two answers like that, exactly the same answers, which are correct actually. You guys are correct. The correct answer is that I have no idea why F equals to MA. I have no idea. Yeah. And do you know? Because if you know, please let me know. Yeah. Because I have no idea. I just know that it is true. This is, in other words, this is how our world works. And why? I don't know. Yeah. Probably if you start investigating that question, you will end up in theology department, yeah, somewhere, figuring out those, I don't know even what. Yeah. So we just know that this is true, and this is what he measured, and we call it. This is an axiom that we do not discuss. Yeah. We assume that this is true, and everything starts working all of a sudden. This is axiom. Yeah. By the way, this is true, of course, when velocity is much smaller than speed of light. Yeah. If we approach speed of light, this is suddenly not true. Yes, because there was a different guy at the beginning of last century. He noticed something else. Yes. Okay. Yeah. Yeah, but since we travel with speed much smaller than speed of light, we say that F equals to ma is true, and we do not discuss that. Was I clear? Yeah. Thank you, guys. You were right, Tom. Yeah, and you were right, Christina. Exactly. Yeah. And this is which Newton's law? First, second, or third? Fourth? Okay. Because you're sure that. Okay. Second, yeah. Do you know the two others? What's the first? What's the first law? Don't say it out loud. What's the first law and what's the third law? Do you remember? Who remembers? I'm not gonna ask you to say it. Who does not remember? Yeah. Really? But you're about to change departments, yes? So we can sacrifice you. No worries. Yeah, guys. Yeah. Okay. Yeah. Okay. Yeah. Yeah. So I just was wondering how many of you know that, because I asked that question a couple of years ago, and not many people. This is second year of university. Many people didn't know what I'm talking about, which is sad. Yeah. Okay. I understand that you understand it, guys. Okay. Let's continue our discussion. And if you don't understand this law, this is your homework. Read about them today. Okay. All right. So what we are gonna do? Our goal is to start from here and to end up here. Okay. So, what did I do? So we will start with projecting this equation on our path. Okay. So we will end up with f times ds equals to ma times ds, right? Let me put ds here. This is ds. This is that infinitesimal increment in trajectory. All right. So can you please start? I'm just going to remind you guys what is ds. I mean, based on the picture, you can see clearly that ds is equal to ds ut, right? Because it has to be tangent to the path. And also our acceleration has such two components. At ut, yeah, in tangential direction, plus the same thing in the normal direction. So just by looking at these two formulas, can you please tell me what is this equal to? Anybody? Yeah. Uh-huh. I need an expression. Give me expression. Perfect. Yes, ds times at. Awesome. Okay, so we can end up with something is wrong with my computer today. For example, okay, I cannot erase this thing. It will stay. Okay, I don't know why. Okay, and you also guys remember that AT is equal to dV dt, or equivalently, it is equal to V dV dt, ds, of course. Okay, so I'm going to, of course, the first one is useless for us today. We are going to plug second one in here. Okay, something is wrong, but okay. So we will have f times ds for the third time, and here we will have mv dv. Okay, and we will integrate. We will integrate from point A to point B. Okay, I will put point A and point B in a second in the drawing. A and B. So A is here and B is here. And you can clearly see, guys, based on these two integrals, that we will just integrate our equation along this trajectory, yes? Along this curve. So, by definition, this expression is work of force F. This is work of force F. Okay, if you want to put it in more mathematical expression, just I usually do U12 of F. Okay, and that's it. We will leave it right there. This is our work by definition. Now this thing. If I remember correctly, this will be equal to 1/2 m v squared from point A to point B. Yes? So that would be 1/2 m v squared B minus 1/2 m v squared at point A. However, I don't use point A and point B in the rest of the semester, okay? I will just replace them with 1 and 2, okay? So that would be 1/2 m v2 squared minus 1/2 m v1 squared, okay? So this is exactly T2 minus T1. Okay, so we ended up with U12 of force F is equal to T2 minus T1. So T1 plus U12 is equal to T2. We ended up with our expression, our desired expression. So in other words, if we start our motion with kinetic energy 1 at point A, and there is some force acting on our body that is doing a work, we will end up with a different kinetic energy at point B, kinetic energy 2. Yeah. Something is really wrong. Okay. Questions to the derivation? Yeah. So work energy is equal to F equals to ma. That hopefully is true. That's the summary of the lecture. Example number 1. Oh, sorry. One more thing before we jump into example number 1. Let's focus on this expression very quickly. F times ds. So you guys can see that in here we have a vector angle gamma between them, yes? Between F and ds. Let's look closer to that expression, okay? So we have F times ds. And I think that by definition, this is F ds cosine gamma, yes? where that gamma is here, between these two vectors, F and ds. Okay, so let's think for a second what will happen when gamma is equal to 0. What will happen when gamma is equal to 90 degrees, and what will happen if gamma is equal to 180 degrees. So in this case, I believe that F is pointing this way and S is pointing in the same way. In this case, ds is pointing this way and F is pointing that way. And in this case, they have opposite senses, yeah, the same direction but opposite senses. Okay, so cosine of 0 is 1. Cosine of 0 is 1, and that means that this is equal to F ds. Yep. Cosine of 90, 0. So that means that such force will never do any work. Yeah, so force that is perpendicular will never do any work. And cosine of 180, negative 1. So that means that this force will be minus F ds. Yeah. Can you give me an example of such force that dissipates energy? Friction, exactly. Yes. All right. So yeah, so friction causes negative work. It causes dissipation of energy. Questions? So example number 1. Okay. Okay, something really happened. I don't have time to fix it. Okay, we will just leave with that green thing on the screen. Please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have a car that starts decelerating. Okay, so that car has mass m. We're going to model that car as a particle. It has initial velocity v0. It is traveling down the incline of 20 degrees. We have kinetic friction between tires and ground equals to 0.7. And also we are on Earth, so g points downwards. Initial velocity is 12.5 meters per second. They ask us to find this distance. They ask us to find this distance. Where velocity is 0, yeah? Velocity final is 0. Okay, any questions? So this is how I solve these problems. So I just write this expression, T1 plus U12, and it is equal to T2. And we have T1, T2, U12. We will find just these three guys. Let's start from the easiest one. What is kinetic energy at the end? 0, exactly, because car stops. What is kinetic energy at the beginning? I think it will be 1/2 m v0 squared. Yes, and now this thing. Yeah, so we have 66% of the problem done. Now let's find U12 of forces. And they told us to neglect all the forces except gravity and friction. Okay, we can do it. However, we don't have to. Yes? Me? It doesn't matter. So they told us to they told us to neglect it. But let's include it, okay? Let's be rebels. Let's not listen to what they say, okay? So I'm gonna include it, and Calvin, the solution will be exactly the same. You will see. You probably already know why. Yeah. So before writing down U12, let's draw FBD. So we have these forces acting on our system. We have mg, because they told us to include it. They told us to include TF, friction, and they told us to neglect normal force, but I will include it. I don't care. Okay. And I think that this is our trajectory. Yeah, this is our trajectory. Yeah, ds points this way. I hope there are no objections. Yeah, ds points this way. Yeah. Okay. So in here we have work of gravity. We have work of friction. And we also have work of normal force. Okay, this is not mathematical formalism, yes? Let's put it in more mathematical formalism, okay? So it will be U12 of mg plus U12 of TF plus U12 of normal force, yes? U12 of normal force, okay. And let's maybe even put it in more mathematical formalism. So let's do U12 is equal to integral from, let's say, A to B, okay, A to B. But you guys later will tell me how to, we will replace these two letters with numbers, okay? So right now, just let's keep their A and B, okay? So we have mg d times ds plus integral from A to B of tf times ds plus integral of AB n times ds. Okay, Calvin, what's the value of the last integral? Or whoever wants to say it. Anybody? No, you're Madeline? Yeah. Yes. And why? Exactly. This is 0 because n is perpendicular to ds. So we can include it, we don't have to include it. Whatever. No. Okay. So now this thing. Let's find these two things, this thing and this thing. Okay, we must find these dot products. So in order to find the first one, I think I must do some projections. And this is theta, by the way. So this is mg cosine theta, because theta is here. And this is mg sine theta. So, I don't know, do you want me to ask you that question? What would be this dot product based on this drawing? Let's go for you, Brian. Yes, exactly. Okay. So we will have U12 mg sine theta ds. And I believe that we also have kinetic friction. So our TF is equal to mu k n, and this is equal to mu k mg cosine theta. Yep. So that would be equal to mg mu k mg cosine theta ds, however with negative sign, yeah? Yeah, because TF points in the opposite way than ds. Okay, and by the way, these guys are constant, yeah? This is all constant. And this as well. Cool, so we just need to find integration bounds. What are the integration bounds? Zero to D, perfect. Zero, D, 0, D. Okay, so our U12 is equal to mg sine theta D minus mu k mg cosine theta D. Okay, 100% of the problem done. Yeah, 100% of the problem done because we found these three things. Yeah, 1, 2, and 3. Okay, 1, 2, and 3. So now I will just plug. The next step is to plug these three things that we just found back into our original equation. Okay, I'm gonna do it. So we will end up with 1/2 mv0 squared plus mg sine theta d minus mg mu k cosine theta d. This is equal to 0. So m cancels out. Yeah. And if you want to find d, it will be equal to v0 squared 2g mu k cosine theta minus sine theta. Plug in values and obtain that d is approximately 25.221 meters. That's it. This is the answer. Okay, questions? So what happened in this problem? We just followed the solution recipe. This is another like solution steps we can follow. However, maybe, you know what, you don't have to remember these solution steps. I will show you some better way maybe next time, okay? We will just modify this expression and I will show you the true solution steps, okay? You can use on the exam, next exam. Yeah. Okay, questions or example number 2? Okay. So let's do example number 2. Yeah, please familiarize yourself with the problem statement before we start our solution. All right, so what do we have in here? I just wanna, as a heads up, the solution will be exactly the same as last time. Exactly the same solution steps. Yeah, I don't know, from interesting things, from the differences, in here we will not use SI units, we'll just use US units. And maybe for the first time, guys, you will see a cubic spring, I don't know. So you're used to linear springs that behave in that way. F equals to kx. This is a linear expression. In here we have fb equals to beta x cubed. Okay, so what do we have in here? We have our boat that is modeled as a particle. Yeah, that boat has mass and it has initial velocity and it goes into a nonlinear spring. Yeah, and they ask us to find initial velocity such that the deflection is half a feet. Okay, so let's find that initial velocity and we can call it a day. So I'm not going to surprise you with this solution, with this expression. T1 plus U12 is equal to T2. Yeah, and second step is finding these three guys, T1, T2, and U12. All right. Kinetic energy at the end is 0. Yes, for the same reason as last time, because our boat stops. And at the beginning, we have 1/2 mv0 squared, exactly like last time. Okay, and now what forces act on our boat? Let us draw FBD. So we have our boat. Actually, you know what? I can maybe write it here. Draw it here, I mean. Why not? So they told us to neglect something, yes? They told us to neglect vertical motion. Aha, so they told us to neglect mg and n. However, since this is our trajectory, oops, this is our trajectory, it doesn't matter. Yeah, you can include them, guys, if you want to. It will not change anything in the solution. Yeah, this is our trajectory, where ds points this way. Yeah. So they told us not to include them. So I don't know. Let's not include them. Let's not include them. You can if you want. And they also told us to neglect the drag. Yes, drag force between the water and boat C. So we will do that. So it turned out that only one force is acting on our boat. Yes, which is spring force. Yeah, this force. Beta x cube. All right. So that will be only work of spring. And let's put it in more mathematical form. It will be U12 of, I think that call it a FB. Yes, yeah, it's FB. So it will be FB. And let's put it in even more mathematical form. So that would be integral from A to B, FB times ds. Okay, and they face opposite direction. They point opposite directions. Yes, so it will be integral of negative bx cubed dx. And integration bounds are from 0 to maximum deflection. Yes, so delta max. And I made the same. I made the same tempo last hour, because I defined not maximum deflections as not delta max but x max. Yes, so let's replace it. And I also tell them a joke right now. 1 hour ago. I'm gonna say it. Okay, so we are going to get rid of. I don't know if you like it or not. I'm gonna say it anyway. We're gonna get rid of our favorite letter this semester at least, and we're gonna replace it with X. Okay. No, not funny. Okay. Okay. What letter will be popular next semester? What do you think? I think it will be lambda. Okay, I should probably I should probably shut up. Yes. Okay. Okay. So our U12 is equal to negative quarter of beta x to the power of 4, 0 to x max. Hopefully I'm wrong. Please, I want to be wrong. Okay, so this is our work, yes? And again, 100% of the problem done, yes? Because we found this thing, we found this thing, and we found this thing. So let's plug them back. Yeah, let's plug them back into our original expression. So 1/2 mv0 squared plus minus 1/4 beta x max to the power of 4 equals to 0. And they ask us to find the velocity, yes? Velocity max. So v0 is equal to probably some square root, yep, of, I believe, 1/2 beta x max 4 to the power of 4 divided by m. Let's plug in values. This is equal to 1/2 3.5 times 10 to the power of 6 times 6. Half to the power of 4 divided by 70,000 divided by 32.2. Yeah. The only reason why I plug these values in, I know that you guys know how to plug values in, yeah, it's just this. Just some of you, not all of you, but just very, very small number of people still forgets to divide m by 32.2 when it comes to US units. Okay, just keep that in mind, guys, okay? Grab your calculators and find that v is equal to 7.093 feet per second. And this is our answer. Yeah. Okay, questions? Yeah. So we can stop here, guys. Easy problems. Yeah. Okay. So we can stop here. Thank you for today and see you on Friday.